All right, so let's see. So that's a long chapter. We're just going to cover some of it. So, two very simple notations before we get going. The number of cases is typically going to be denoted by little n, the number of subjects that I have, the number of rows, the number of units that we have in the study. And then the number of features or variables is always labeled here by k. So, it is important to understand what's the relation between k and n. If n is bigger than k, this kind of situation is called an overdetermined system because you have more equations than unknowns. If k and a are equal, you've got a perfectly determined system, and if k is bigger than n, you have an underdetermined system. Okay, is everybody here with me? You have a lot more features than actual cases. Think about genetic studies. Hundreds of thousands of SNPs, and typically you're lucky to get, I don't know, 1,000, maybe if you're lucky, 5 to 10,000 subjects. You know, 500,000 SNPs. You know, a lot of variability encoded in the system and relatively few constraints. So that's why the system is underdetermined. So there are techniques to deal in all of these situations, obviously. For instance, when n, the most common case is n is bigger than k, right? Everybody understands that. The number of subjects is much bigger than the number of known quantities about the subjects, right? That's the usual situation. You typically have, 100 subjects, and you have a dozen, maybe 2 dozen biomarkers. So think about what the linear model, for example, least squares, looks at these things and it says, well, you can't fit a perfect model because your system is overdetermined, but you can fit an approximate model that, roughly speaking, minimizes what? Well, it minimizes the distance between the model predictions and the actual values. So you have this, every person is a unit, and it pulls out this regression line, and the regression line stays in some kind of an equilibrium in between, and the model is not perfect descriptor because it can't perfectly describe for every subject. The system is overdetermined, but it is a description. In the case when k is bigger than n, it's a little bit tricky, so you gotta strategically deal with this. And when they're equal, there could be a unique solution, not guaranteed, but there could be a unique solution, because some of the cases could be equal, and then things like rank order of these matrices come into play and whatnot. All right, so this notation, well, let's just, the response vector y1 through yn for the n subjects, the design matrix, the features are the columns, and then you have for the n cases, for the n subjects, the feature 1 for the first subject, second subject, third subject, n subject, feature 2 for first, second, third, etc. subjects are kind of represented in this design matrix. So the basic idea is that ordinary least squares, if you do linear modeling, you essentially minimize something that looks like this. You find the effect sizes, the impact of the features, by trying to minimize the discrepancy in this linear quadratic distance norm. You minimize the discrepancy between observed and predicted values, right? And you minimize this over the effect sizes, and this has nice closed form notation. Hats are estimates. The beta estimate, ordinary least squares, is just given in terms of design matrix. Transpose of the matrix times the matrix, that's a square matrix, take the inverse, multiply by the transpose, and multiply by y, and then so you have a solution there. And in a situation where we are dealing here, what we're going to do is we're just going to add up. So this is called a fidelity term. The fidelity term allows you to match observed and predicted. That's fidelity. How good is the model? But in the linear absolute estimate, what you do is you add up an extra penalty term here. You've got the fidelity, but you're putting a regularization term with certain coefficient. You control what's the weight of this penalty term. And the L1 norm essentially takes the magnitudes of these coefficients. So in other words, to minimize this, you have to have a good match, and you want to have as few large effect sizes as possible. Is that right here with me? Because if these effect sizes are large impacts, they're going to add up to this, and you're going to be far and away from the minimum. What you're trying to do is you're trying to reduce collectively all the effect sizes. So remember, this is the effect size for the first variable, the second variable, etc. So it's just absolute value of beta 1, beta 2, beta 3, etc. And this coefficient kind of tells you what's the impact of the regularizer term next to the fidelity term. Now, you can also have a closed form notation. Now, it's very nonlinear. You have this max function here. It's a nonlinear solution, but it can be expressed in closed form mathematical terms. You can also look at not the L1 norm, but the L2 norm, where you essentially square all the effect sizes, okay? And that's called ridge regression. The first one that used the L1 norm, the absolute values, is called lasso regression. This also has a closed form, and there is a third one that's called OMP, for orthogonal matching pursuit. You want to use the zero norm, which simply says reduce the number of non-trivial effect sizes. So all the effect sizes should be zero except very few. This is the number of non-trivial effects. The L0 norm, number of non-trivial effects, L1 norm, the sum of the absolute values of the effects. L2 norm is the sum of the squares of all the effects. This is the penalty that you add to the standard fidelity term to get what's called regularized linear modeling. So let's just look at one example here. In this case, this is a simple data set. Yeah?
So L0 norm is generally used for sparse solutions. L0 norm for sparse solutions. So here, where sparsity is coming in?
The sparsity is going to come in when in two ways. First of all, many of these X things that are in the design matrix could be sparse. The design matrix could be sparse. Remember, it's this K by N matrix can be sparse. But I'm not sure if you're referring to the sparsity of the effect sizes or the design matrix. Typically, people mean the design matrix, the data, that is, needs to be sparse, but
it can be beta also for sparsity.
yeah, so well, all of them are trying to minimize the energy of the betas. But the question is, how do you measure the energy? Because the energy of a vector, you guys, think about a vector. Beta is just a vector of coefficients that tells me the impact of every one of my features. But its energy can be measured in uncountably many ways. One of these is simply to count how many non-trivial betas have I got. The maximum is n, the minimum is 0. It could be anywhere in between. The energy can be measured by adding up everything in absolute value, which is the L1 norm, which is the lasso. The energy can be measured by Euclidean distance, which is the L2 norm, which corresponds to the ridge regression. The energy can be measured in general by Minkowski's distance, which is the LP norm. So, you know, you can do a variety of things to measure distances.
Sorry, I didn't get the effect size thing.
The betas are called the effect sizes, so they essentially tell you what's the impact of, because remember how you have right up here. So imagine the vector, I think I have this later on. So the vector B is right up here, beta 1, beta 2, beta 3, beta 4, beta 5. So to get a prediction for the response Y1, This is the actual value that's observed. But to get y1 hat predicted, you're going to multiply all of these guys. So, you know, you're going to multiply for subject 1, feature 1, feature 2, feature 3, feature k, effect size 1, effect size 2, effect size 3, effect size k. Right? So you multiply them, and that linear combination is going to give you the y hat predicted. So the effect sizes are essentially how you linearly package the inputs to generate the output. Yeah.
N1 norm. Just suppose we are talking about regularization. I don't know. N1 norm is applied to a matrix that we want to make the matrix sparse. I mean, once L1 norm applied to a matrix that is dense, it goes through the sparsity. However, if the matrix already is sparse, L1 norm is not working very well there. We should apply it to.
That may be the case. That may be the case. The question that he's posing is, if this design matrix is pretty sparse, should we use the L2 norm instead all the time? I'm not sure if there is a general principle that states that if X is very sparse, you got to use L2 instead. All of them now. The L1 does tend to pick fewer betas. Whereas in the ridge regression, you're likely to have a lot of small. In fact, most of them are probably not going to be 0, but they're going to be small in magnitude, but still play a role, I guess. Again, I'll show you guys example. You may want to do both every time and see which gives you a better result at the end in terms of the validation error. Okay, so this data set here has, okay, so this is the baseball. So it's got 1,034 observations and 6 features. The features are, you know, the name of the player, the team that they play for, the position that they play, their height, weight, and age. And in this case, we are going to use the first 900 players. These are, again, we could have randomly sampled here, but let's just pretend they're randomly mixed. For example, if they're alphabetically ordered by their name, they could as well be alphabetically mixed. So right up here, suppose we want to predict the weight in terms of the age, and the height of the player. And then y is going to be the corresponding outcome variable, which is continuous weight. And you could do the same thing for the remaining case. We're going to call them x test and y test. The GOM net package provides the functionality needed to fit in both lasso and ridge regularized regression. And now here is the cross-validation. We're going to talk about cross-validation a little bit later, but roughly speaking, we do, the method is CV for cross-validation, and then GOM net, you provide the testing, the training that is, the training model, predictors, and the training model outcomes as inputs. And then you're going to use the mean square error. There are different types of error measures that you can use. You can use accuracy, mean square error, absolute deviation, whatever. And alpha equals to 0 corresponds to ridge regression. You can specify here alpha equals to a column vector of values. You can do C 0, 1, and it's going to fit in both of these. If you put in alpha equals to 1, that will correspond to the lasso regularizer, the L1 norm. And if you use alpha that's between 0 and 1, this is called elastic net regularization. When you blend them, elastic net gives you an alpha in between. And then here is the corresponding coefficients. And here is the, remember how we have one coefficient lambda that controlled the effect of the regularizer? You can kind of print this and kind of show you. So if you have log of lambda is on the x-axis, and then it shows you at what point, if you use a large, log of lambda, then you see the first coefficient gets truncated at about log of lambda equals to 6, and they're both truncated when log of lambda is equal to 8. The vertical axis is the magnitude of the coefficients. So you see the red one, I forget which one it is. One of those is the age, and the other one is the height. Okay, that's a slightly better plot. There is another package called plot mode that actually allows you to label, so the height and the age. So the height is the black one, the age is the red one. You can print the coefficients as well. And now notice how they are very, very small. That's interesting. And then you can report the minimum lambda. And we're going to call this lambda best. And then once you have the model, you can actually do the prediction on the remaining 100 or so players. You plug in the model, and then the new x that you enter is the testing data, and the s, the lambda parameter, we're going to use this minimum lambda that we have before. And then you see at the end we need to quantify how good is the model. So remember, we're predicting, was it weight? We're predicting the weight, exactly. Y is the weight. And then, so to validate the model, we are going to compute the root mean square for this ridge regression by subtracting away the test weights of these individuals and the predicted weights. So find their sum square deviation. This is the squaring of each individual for each individual of these 100 subjects. And then compute the mean of these and report the ridge regression root mean square. It ends up being 264. We're going to see what this value means. By itself, it doesn't mean anything. It simply means that on average, we are about 264. If you take the square root of that mean, 264 is, 266 is 196 is 16, is it? 16. Yeah, so it's about 16 or so. On average, we're about 16 pounds, I believe these measures are in pounds, away from the actual weight of the individual. So this by itself, it does have some meaning, but it's more interesting when you compare it against another model, like, for example, the lasso measure for the same data set. You can also compute the corresponding R square, the coefficient of determination. We are kind of manually computing it here. And let's see if we did this. So in lasso, again, the least absolute shrinkage and selection operator. For the same data set, here is where we specify lasso is the lambda equals to 1 parameter. and our root mean square is 261. Remember, the other one was 264, so the lasso regularized model has a slightly lower, not much, but slightly lower error rate overall in RMS root mean square measure. And I believe we also fit in the ordinary least squares. So the R square values is what's plotted here. So you can see that the explanatory power of non-regularized linear model is a little bit lower than the regularized linear models. Now, whether one of these two works better, well, you know, they're roughly speaking on the same scale. Again, if you print the error rates, the best is lasso followed by ridge followed by least squares. Okay, so let's press on here. Bias and precision, variable selection. So, by the way, the regularized linear models that I'm showing you do a joint model fit-in and variable selection, right? Because as you zero down the effect sizes, as you have fewer effect sizes that are non-trivial, it effectively does variable selection for you, right? The non-trivial effect sizes correspond to features which seem to be predictive, and the effect sizes that are truncated or marginalized by the regularized regression correspond to features that can be excluded from the predictive model at the end. So it does a joint model selection and feature selection and modeling. Okay, so that may be an interesting study. Neuroimaging genetic study of Parkinson's disease. Oops. Oh my gosh. Clicked on. How do I stop that? Finished. Okay. So you can look at the data. Basically, it includes a subject identifier followed by a whole bunch of neuroimaging derived biometrics all the way up to here. For example, this one is right putamen, the size of the right putamen. There is probably right putamen surface area, left putamen, etc. Just a few regions are added here. You've got some demographics, gender, weight, what research group they belong to in this Parkinson's disease study, their age, a few genetics biomarkers, and then the clinical results of the UPDRS, Uniform Parkinson's Disease Rating Scale Part 2, Part 3, and then the time of the visit of these individuals. There are missing values in these data set. So what we are going to do is we are going to load it in, extract the complete cases, and then do a little bit of reporting for, apparently 34% of or so of the data might have missing. And suppose you want to predict, so in this kind of situation, okay, oftentimes the clinical variable of interest is not given as a single column in the data. It's a derived measure. So that's what I'm trying to simulate here. I'm saying suppose the outcome that we want to predict is a variable y, but it's simply the aggregate of the clinical assessment, namely these three parts of the UPDRS scores. Collectively, jointly, these represent my outcome variable of interest. So that's a new value, and you can just print a few of these just to see what they look like. Quite a bit of variation, as you can see, as to the total UPDRS scores for these individuals. And then what we are going to do is we're going to remove some of the features. So features that are irrelevant, I don't want to use them as predictors. For instance, the subject identifier has nothing to do with the prediction. I want to remove the things that I'm using to construct my outcome variable, right? I'm removing these guys. And we're also removing the research group, because the research group is highly correlated with the actual Y variable that I constructed, right? I could have used the research group as an outcome as well, right, if you wanted to. And then what we're going to do is we're going to look at this nice syntax, all the features that we're going to be using for all the subjects, except that this bang means exclude the names of the columns that are in the dropped features set. So we're removing this with all the other features that you saw earlier we're going to be using in the model, and then we're going to be casting that object, not as a data frame, but as a matrix, and then only using the complete cases, not to worry about missingness. We already talked about missingness. You can use multiple imputation to impute if you want to. Let's not worry about the missingness at this point. And then a summary of X, kind of reports what features we have and some of their main quantities. All right, so here we're going to split into 20%, 20%. That's a common strategy. Train on 80%, test on 20%. Exactly the same strategy as before. 80% corresponds to 4/5 of the number of rows, randomly sampled from all the rows. So the testing data is going to be the indices that are not in the training. And then training data is the X and Y that have the training indices. Testing data is going to be the X and Y that have the testing indices. And then for the X-train ordinary least squares matrix, we're going to column bind these training with a corresponding index of the number of rows. So here is where we're going to, the ordinary least squares fit is going to be very simple. We just call the linear model, and we predict the training outcomes from the training data. That's it. For the ridge regression, we're going to use the GOM net with alpha equals to 0 without any additional parameters, very out of the box. For the lasso regularization, we're going to use exactly the same X training and X training and Y training, but alpha is going to be equal to 1. And then obviously we can compare the results of various metrics, accuracy, root mean square. In this case, because the outcome variable is continuous, right? It's actually discrete, but we can think of it as being continuous. There is no such thing as accuracy, because your predictions are never going to be, when you have a real value, you can never predict exactly the same real value, right? You're going to be in the vicinity of that real value. That's why you got to compute something like the root mean square or correlation. We saw correlation earlier to assess how good the models are. So okay, so very briefly about these paths here. So once we fit the model, we can plot them. So this shows you guys, look at this graph for one brief second here. So this shows you a log of lambda, and the lambda was the magnitude of the regularization term. Remember this lambda that multiplies the L1 norm of the effect sizes? If this lambda has a log that's anywhere between these values, that's on this axis. On the top axis, you essentially have how many coefficients survive. Remember, we had 20 or so predictors, and if your penalty term has this, you're going to be including quite a few of these coefficients. But as your penalty increases, you're going to be having fewer and fewer. And typically, if you have 5 coefficients right up here, 5 coefficients that survive, these are going to be corresponding to the, you can read their value here. This is the size of the coefficient. So you see how they all tend to be 0 as the impact of the coefficient increases. Because remember, you're minimizing this joint two-term expression, okay? And this is minimized only when both terms go down to 0. But as you increase the penalty, you have to decrease the number of betas that survive that threshold for the lasso. If you do the same thing for the ridge, now notice how the penalty terms are slightly different, and that's interesting. You see, they all tend to 0, but they're never almost exactly equal to 0. You need to use all 27 of them. So this sparseness that she mentioned earlier with the ridge regression, you still need to use all of them. You need to use all the predictors to get your response. And sometimes the interpretation of these models that have lots of features that predict is more difficult than models that have a few features, even if you compromise a little bit the overall root mean square. The fact that you have a simpler model may be more powerful than the fact that you have a more accurate model. You know what I'm talking about? So you have to trade off a little bit. So they do tend to 0 always, right? But let me see what's... Okay, so you see, even as you increase log of lambda here, they tend to 0, but they're not exactly trivial. Okay. So I think, do we have... Okay, that may be an interesting plot to look at. Geometrically speaking, what's the difference between the lasso and the ridge regularizer? So in the case of alpha equals to 0, you have the ridge regularizer. It corresponds to a topology where, you know, the AOS coefficient is over here, and your target is over there. So the point of contact is never going to be at exactly one of the axes. Whereas for the lasso topology is this strange diamond shape topology, and you see you're hitting you're either on or off because of of how the geometry kind of works out here. The point of contact is exactly at one of the axes. So in other words, here you guys, here you have to use two coefficients, because the optimal value is right up here, and it requires this and that coefficient, whereas in the lasso, one coefficient is enough. You can't touch the border here where you require both coefficients. Only one of them suffices. And you can see how this changes here. We plotted several of these as you change from, remember, elastic net is this kind of blend where your alpha that you include in the GOM net is not discrete 0 or 1, it's a blend of them. And if you use lambda equals to 1/9, for example, you see how it begins to go from the circle topology, which is the nice Euclidean metric for distances, all the way down to the lasso, which is the diamond, very sharp edge topology. It begins to migrate, and you can see, you know, the natural progression of this topological change that leads you from one extreme to the other, in a way, geometrically. All right, there is a little bit about, okay, so the cross-validation. So in the cross-validation, remember how we coded early on, we had this CV for cross-validation .gom net. Well, what this thing does is it randomly splits the data into n parts. So if you use, 10 folds, for example, that is going to correspond to splitting the data multiple times, splitting the data into 10. One of those gets reserved for validation. The other 9 parts get used for the training. So this is a 90-10%, 90% 10% split, corresponds with n equals to 10. If you use 20, obviously that's the corresponding thing. And then you fit in the model on the n-1 training sets from multiple lambdas, and then you create the prediction metrics, accuracy, MSE, etc. And then you repeat the process, and at the final end, average the prediction methods across the iterations. So at every iteration, every case, every subject is used precisely once as a testing and multiple times for training. Because remember, if you have 10 subjects and you use 10-fold cross-validation, the first time this subject is going to be the one that you test on, and all the other times they're going to be the one that you train on. So repeating the process multiple times and averaging, this is very important, the prediction results, whatever the results end up being, they could be yes or no, they could be RMSE, accuracy, you know, whatever. You average these across, and that's the reported cross-validation error that gets reported at the end. So you don't manually split the data into testing and training. The cross-validation does this. You only say how many folds do you want to use in your CV. Okay, so here again is the actual method, CV GOM-NET, and for the corresponding ridge regression as well. I thought I had a plot here. This is the least squares. Okay, so the final models, the comparison of the final models. Here is where we compute the test case mean square error for the 3 models. And here is a graph. This is called a variable importance plot, a VAR plot. It kind of rank orders the important features that are predictive of your outcome, and it gives you the corresponding coefficients. Now here, ordinary least squares is black, lasso is red, and ridge is in blue. Now, remember, the ridge is the one that had this kind of strange behavior. It leaves all of the coefficients in, although they do become small, you see. They do become small, but they all stay in. Lasso is the one that keeps only a few of these in, and most of the other ones are zeroed down. And ordinary least squares, it's all over the place, right? So, in terms of feature selection, lasso is the more conservative. Yeah, the more conservative because it uses fewer of them. Then comes ridge, and then comes the ordinary least squares. And there again, all of them are kind of converging down to 0 because you rank order. So, demographics, genetics, some imaging, they all come into play. Okay, so that last part here is also very interesting. It's a fairly new technique that was invented about a couple years ago by a group at Stanford, Emmanuel Candace and his colleagues. It's called knockoff filtering. It effectively, yeah. The question, okay, so is your question, is it true that if you have a very large data set, you don't have to?
Yes, because regarding the deep learning that you are looking away from, many large scale data sets usually spinning to the next one, and there is no cross validation going on these kind of techniques on literature, and I can see by looking at why, and there is a part from the benefit that yes, usually because are not supposed to have a small data, a small case data, a small scale data. So cross validation is not working at just why mathematically.
Well, I mean, obviously on the asymptotics, if the size of your data increases, you don't need cross-validation. Why? It's very simple. Because as the size of the data, and that's why people are so hot about big data. Because as the size of the data increases, we're not looking at a sample anymore. You're looking at the entire population. So you don't have, there is no, the cross-validation is a technique that allows you to take away the sampling effects that may be present. But in a very extremely large data set, there is no sampling effects. You're literally looking at the population. Now, there is other problems that arise with large data sets. one of which is obviously control of reliability. Because think about it, you know, in the US, for example, there is a very strong push to go to a statistical census of the population and not really try to touch down every single household. Because trying to monitor the entire population is very difficult, very expensive, and very inaccurate. You're bound to have errors. And these errors, magnified by a large scale, introduce potential for a very substantial bias, which is not going to be present by a very censored census of, you know, 10,000 households, but making sure that you don't commit any sampling error. So, you know, it's one of those things where you have to weigh in the pros and the cons. Again, if you have an extremely large data set, you probably don't have to worry about cross-validation. I mean, we tend to always do it though. Cross-validation is not going to introduce a problem other than the expense, because these things get expensive pretty fast. If you have a large data set, cross-validation can run for days. So other than compute power and time and energy that goes into that, it's not going to introduce a problem by itself, cross-validation. But whether or not it's going to add anything, well, you know. All right, so let me briefly tell you about the knockoff method. It is a very interesting one, and we're trying right now to do a bit of a comparison, contrast knockoff with a new method that we're developing called compressive big data analytics, or CBDA. So in the knockoff method, the basic idea is that we want to do controlled variable selection. Okay, you want to do the variable selection in a way in which you have certain confidence level that features that need not be included are not included, and features that have to be included are included in the final model. So it's a bit tricky, okay? How do you know when you do the regularized regression? How do you know that the really important features are in and the really not important features are not in? Okay? Because this is always going to be the situation, right? You're going to have a blend of important features and non-important features, and you're always going to be committing one of these two error types. Features that are not important are included, so this is false detection, and features that were excluded were supposed to be in. So false positive and false negative inclusion errors are going to be committed. So the knockoff filtering answers the question, can we be certain within, let's say, 10% that our error rates are controlled? No matter how many features we have, no matter how many cases we have, we want to control the false positive and false negative rates. Okay? So it does it in 3 steps. So I'll just give you the heuristics, and then we're going to do an example perhaps. In the first step, it looks at all the features, the real features, the X predictor variables, and for every one of these real features, it puts in a fake analog. So for X1, I'm going to have X1 fake. For X2, I'm going to have an X2 fake, etc. So it pairs up all the real features with fake counterparts. And the knockoff, I'm not sure if you're familiar with this term. I'm personally not a huge fan, but the authors of this method have called it knockoff. Knockoff refers to a product that's not quite original. You guys probably know. You know, not my favorite term, but that's what they've chosen to. And the designer bags, you know, is what they use as knockoff. You know, Gucci or one of these things. You know. So, but anyway, so in the first step, you kind of pair up each of the real features with a parallel that's non-real. And for each of the, so by the way, the real features are going to be called xi's and the fakes are going to be xi tildes. So for each feature, we're going to be computing some kind of a knockoff statistic wj, which measures the importance, the importance of the variable relative to its decoy counterpart, relative to its fake counterpart. Okay? And I'll tell you how this can be, yeah.
What exactly means non-real? I mean non-real counterpart.
No, not necessarily non-linear. The process is, I don't believe the process is non-linear because some of the thresholding is very non-linear. I'm referring to measure the importance of xi to xi tilde. We'll see how this is done in a second. It's not necessarily linear or non-linear. And then in the third step, you're going to determine an overall knockoff threshold values by computing the rank ordering of the WJ's statistics from large to small. And essentially you walk through the list of the WJ's. Every WJ is paired with a real and a fake XI. And you're going to be selecting the WJ's corresponding to positive statistics and terminating this search the last time the ratio of the negative to positive WJ is below a specific false discovery rate Q that you specify on the beginning. So you start this process with fixing a Q FDR value of typically 0.2, 0.1, something like this, not too small, because if it's too small, it's 0.01, you may not get any of the features selected. So whatever the FDR, so here is the false discovery rate mechanism for these feature selections. And so these are the three steps that the knockoff method goes through. The importance is up here, exactly what is this WJ statistic that corresponds, I'm sorry, it should be an I. It's WI statistic that corresponds with every XI and XI tilde pair. And the rest is kind of pretty much static, right? Once you have the statistic, ranking them, that's easy. Selecting the last WJ where the ratio of the negative to positive WJs up to this point is equal to the predefined level Q. So just to give you a little bit of intuition of how does this thing works, a variable J is said to be unimportant or irrelevant to the prediction of the outcome Y whenever it's orthogonal to Y knowing all the other features. So in other words, this orthogonality means independence in a way. So if Xj is independent of the outcome when you know all the other features, it means that Xj is not contributing anything to Y itself aside from what was already contributed by the other features. Okay? So, so the basic idea is that false discovery rate computes the expectation, in other words, the mean of this ratio, the number of J's that belong to S hat, where Xj is unimportant, so the number of unimportant features divided by all the features, and you're looking for the expected value of this, and you want to control, here is the upper bound, this FDRQ value that you fix a priori needs to be an upper bound for this expectation. So here is an example that comes directly from their paper on the knockoff. Suppose you have 1,000 observations and 300 variables, and suppose you have 10% of these. 10% of these are real signal, the other 90% of these 300 variables are noise. Does everybody see that? So you have Q in our case should be 0.1. So what we're going to do is we're going to generate n times p random normal features, okay? And we're going to split them into n rows and k and p columns. So you see, you construct a design matrix that is the number of rows is the cases and the number of columns is the features, but you generate in one row. This is kind of shorthand notation. By generating the product, which includes all the cells in this matrix, random normal variables. And then the non-zero, you're going to choose which k of those, which 30 of those are going to be from the 300 are going to be non-zero indices. And then the non-zero indices, you see for the non-zero indices, the betas, we're going to amplify the noise, okay? This is my way of selecting. Remember, because we sample from random normal distribution, to get something that's 3.5 or bigger standard deviations away is very atypical, yeah.
How is it very different from RFE, recursive feature elimination? Because in that also it eliminates the last one, what it is doing.
Right. Recursive feature elimination is very different. In recursive feature elimination, you start with all the features and you iteratively look at subtracting one of these features based upon, essentially you rank order them at the end of each iteration, and the least important ones you sift out, and you have some kind of a stopping criteria that says, well, stop when the error rate is too big or when you have fewer than n features or something like that. It's very different here. Yeah.
It's similar in a way, like the one which is contributing less to the model is eliminated because it is random.
Right, but you see, in this case, in recursive feature elimination, you never know if the features that you got at the end, you never know if you get 90% of the features that were real in the model. You don't know that. Because you see, sometimes features of small effect, small magnitude, may actually be very important. And they may be triaged by mistake. You know, there is a little bit of stochasticity in that process. In the knockoff, they've worked out the math and they proved that they're guaranteed to have at most Q false positive results, false positive features in the model, which is, you know, comforting, I guess, to some extent. They don't have to be the biggest in magnitude features. You know, I mean, it's a different logic, I guess.
If the features are voxel with some intensity, how will be the fake counterpart will be made?
Right. So, well, this is the essence of the knockoff algorithm. They have several different protocols for generating the fakes. In essence, you guys, what do you want from a fake? From a fake variable, you want the following, okay? You want this variable to resemble the variable of interest. So fake, non-fake. Real. Reals are over here on my left hand. The fakes are on my right hand. The way you select the fakes is by looking at the variable, the real variable characteristics, mean, standard deviation, skewness, kurtosis. Look at some of its characteristics. Try to resemble these here, okay? And then look at pairwise relations. The real variable may be highly correlated with some of these guys. So you want to preserve some of that here, but at the same time, you want all the fakes to not carry additional information. So you want them to be randomly sampled, let's say from a normal distribution that has the mean that your real variable has, but it doesn't carry the signal that the individuals in the real variables carry. So in other words, it tries to resemble the characteristics of the real features, but it doesn't have signal in it. So just like I'm introducing artificial signal here in the non-zero in these K that we have, we're introducing a little spikes, you know. The fakes are not going to have these spikes, right? So, and it is very interesting. It's an orthogonal way of thinking about feature selection. The recursive feature elimination is one way, and you can do it from top down, bottom up. You know, this has been worked out for decades. That's a fairly new kind of looking almost from the other side, from the frequency point of view, I guess. So you're going to introduce some of these amplitudes, and obviously, if you want, you got to be careful with this. Not too high, not too small. If it's too small, it's almost not going to make a difference. If it's too high, it's going to be obvious. So you want some effects artificially introduced in the data, and then we're going to see if we can recover that. And then you sample essentially. You sample the responses by multiplying by, you see, getting the betas, corrupting it with noise, and then that's going to be our sample. The knockoff package you need to load in, and then the calling is very simple, right? So Y is going to be our Y sample, and then the knockoff filter is the method you call with the design matrix and the corresponding outcomes. And then if you print the result, it kind of tells you that the selected variables are indexed right up here. These are the indices of the, remember there were 300 features. We selected, I don't know how many there are, 25 or so in here, or 30. And you can compute the actual false discovery rate by this function. And the actual false discovery rate is 9%, right? So in other words, 1 or 2 or 3 of these indices are not matching the randomly introduced spikes of amplitudes that we made within these. So we did include, you know, a few fake things, but we, roughly speaking, are below the self-imposed upper bound on the false discovery rate. So, you know, it is, the beef of this method is exactly how do these WJ statistics work in practice? How are they defined? They have, you know, roughly, so here is one example that they do. They do the maximum of the, remember the fake and the real, they take the maximum of them all, and then they multiply that maximum by the sign of the difference. Okay? So this is a statistic that effectively measures how much more important is WJ relative to WJ tilde. So for example, you know, the bigger the difference is, they might be with corresponding difference of signs, or the magnitude here can be different. Okay, and you can control the choice of the statistics. They have coded several ones, alternative ones. Here in this example, for instance, we get an FDR of 15%, even though we requested a 10%. Do you have a question? Yeah.
Yes, Dr. Dinov. I was a little lost when you mentioned, you know, we have the real and fake. So this one, because we have to preserve the characteristics of that, assuming that this is normal, that is also normal. So I didn't get the part when you said we introduce the spikes. So how do you introduce the spikes?
No, the spikes I only introduced in the simulation that I did to prove that the knockoff filter, the spikes I only introduced here artificially, right? Or over here I introduced these spikes of amplitude just in this simulated example, right? In the knockoff, it doesn't introduce any spikes. It's trying to infer the spikes. In other words, from the 5 real features, maybe only 2 of them are real, the other 3 are not important. But we don't know which 2, or we don't know how many. So the logic is that when you don't know, you go ahead and generate fake counterparts, and then compute some of these WJ statistics that tell you the relative importance, rank order them, and then start with the big ones. They're going to stay in until the change of these WJ becomes smaller than this Q value, and then you stop. You say, okay, the top ones are the ones that I need to choose, the other ones I can discard. So it has the theoretical property of preserving a false discovery rate at a controlled rate. That's why it's called controlled variable selection using knockoff. So the spikes had only to do with this simulated example. They're not. The spikes were essentially trying to introduce real effects in a simulated data set, if that makes sense.
So it's not really introducing spikes into the...
No, it's not, right. So, in fact, the fake variables, they're supposed to be completely random. In fact, when the observation is up, this can be down because it's stochastically chosen from... It just wants to preserve, roughly speaking, the behavior of the process. Okay? And I think I had a little diagram here that shows... Maybe it's at the end. So, this is an example with, I don't know, maybe... I'm not sure if there is going to be time. This is just an example with the Parkinson's disease data set. We're just calling the knockoff, doing again as we did before, the variable, the design, summary. Let's see, where is the... it talks about binarization. Well, yeah, this is probably an interesting, this kind of shows the logic or the foundation of false discovery rate as a criterion for selection of, it's originally designed to select p-values, okay? But in the knockoff case, it's used to control the probability, which is a p-value, of selecting a wrong feature in the set of features that survive the knockoff filtering. So the false discovery rate is the expectation of the ratio of false positives over the total number of selection features. And just to give you one example here, we have 14, suppose these are 14 values rank ordered large to small. And then suppose you're targeting an alpha star of FDR of 0.05. You sort the p-values, print them out, and then calculate the threshold for each p-value by multiplying the relative size over the length, and then you see all these p-values that we had from 0.01, I believe, right up here. From 0.01 all the way up to 0.9, the corresponding p-value thresholds are computed through this formula, and you see the final boolean that kind of compares whether or not the p-value survives is given as this index 0 or 1. So in this case, you only have one of these that kind of passes the threshold out of the 14. So, all right, so that's probably a good place to stop. That's just an explanation of FDR graphically relative to Bonferroni correction. And did we run the knockoff? Oh yeah, so we finally run the knockoff filter here for the Parkinson's disease data, remember, at the end, and it tells us that knockoff selected are these, how many? 8 features are selected by the knockoff, and then this is the Benjamin Hodgberg selected are in the second set that gets printed, their common intersection is these 4. So 4 out of the 8 or so coincide between 2 different feature selection methods. So here's the example, and recursive feature elimination could have been yet another method. And you typically would run several methods and see if they agree. If they agree only 50% as they do here, you may want to do some soul searching. Obviously, the features that agree on, they got to be part of the model. From the ones that don't agree, you got to maybe apply clinical relevance to either select or exclude some of these to be part of the model. It's not just statistics, right? It's just, remember the difference between practical or clinical significance and statistical significance. They're very, very different things. Something may be very highly statistically significant, but its impact on the patients could be marginal. It doesn't mean you got to start treating people simply because there is a statistical significance, right? So you got to weigh in a little bit of both the contextual importance of features and their statistically significant importance to be included in the model. So this is just an example with 2 of these feature selection methods. Yeah.
This feature is selected by knockoff. Is selected supervised or unsupervised?
No, they are unsupervised. They're unsupervised, right? They're completely automatically selected without any relevant. It just looks at, you know, the relative importance of decoy variables versus the real variables. All right, so any other questions here for this? I know we didn't work all the examples, but it's probably worth it going over if you have a situation where you have lots of features and you do want to do selection. And by the way, knockoff, you know, it's fairly, again, the reliability there comes from the fact that you're almost guaranteeing yourself not to include too many features that are irrelevant.